Okay, I'm going to talk about some complexities in stoichiometry, specifically focused on limiting reactant. So this is something you really deal with in everyday life, say when you're cooking. Um, you don't use up everything in your kitchen when you're cooking. Now there may be a certain ingredient that you run out of, so maybe you don't have quite enough of it, so you have to scale down your recipe or something, but whatever ingredient you're running out of, that is what we would call the limiting reactant. So we're going to talk about how you determine what the limiting reactant is in a chemical reaction. But before we jump into examples, I just want to make sure that it's very clear what limiting reactant is, how we could quantify it, but also compare it to one other thing. Specifically, let's compare it to what we would call stoichiometric amount. So we could have a chemical reaction that we perform where we have a stoichiometric amount of substances, or you can have a reaction where you end up having a limiting reactant. Okay, so these are kind of your two possibilities. Sometimes it's explicitly stated, sometimes it's not, and you have to assume, and sometimes you have to do calculations to figure out which situation you have. So a stoichiometric amount, it just means that you have the same ratio of reactants as your balanced chemical equation, okay? So your balanced chemical equation essentially gives you the ratio of substances that you need, okay? It's your foundational recipe for a reaction. And so it tells you, say, for one of these, you need two of these, okay? And you can either think of it in terms of molecules or in terms of moles of those things. But just because the balanced chemical equation might say that the ratio is 1 to 2, it doesn't mean you need exactly 1 mole of the one thing and 2 of the other. Okay, it's just the ratio. So you need the proper ratio to have a stoichiometric amount. Okay, so this means that if you were to do a reaction with this stoichiometric amount, it means all of the reactants are going to be consumed. Okay, there's no excess reactants, meaning no reactants left over in the end. Okay, so sometimes we do that, but sometimes that's just inconvenient, trying to measure everything perfectly and quantify everything. We don't necessarily need to do that. Very often we're dealing with situations where something's the limiting reactant. Okay, so something we measure accurately, and then everything else we just make sure we have enough. Okay, and so the limiting reactant is the thing that is limiting how much product you're going to get. Okay, so typically we would set up a reaction, and whatever the expensive substance is, we would quantify that. We would measure out how much we need, and then the other stuff we'd just throw in extra just to make sure that we use up all of that other expensive substance. Okay. There can be other reasons, but that's a pretty common situation why we would not want to waste this one reactant. So we want to make sure we measure that pretty accurately, and then just make sure there's enough of the other stuff. So in this, the limiting reactant is going to be completely used up. And that means everything else would be called an excess reactant. Okay, so everything else, there's some left over in the end. Okay, so you either have a stoichiometric amount of stuff or there's a limiting reactant present. Okay, so either you put things together in the perfect proportions, like you would do when you're cooking something, right? Or theoretically. And then you can also just instead have a limiting reactant. So to where you put in the right amount of one thing and extra of the rest. Okay, and so a lot of stoichiometry problems deal with limiting reactants, and they may not directly tell you. Okay, so sometimes they only tell you about one substance. If they only tell you about one substance, it's because the other stuff is in excess, or there's at least a stoichiometric amount of them, and so you don't have to worry about them. But if they tell you something about multiple reactants, like they tell you how much of each there is, then you need to be careful because one of them may be limiting. And if they don't tell you that something's limiting or you have a stoichiometric amount, you have to figure out if there is something limiting, because that's what's going to guide your calculations. So how do we determine if something's a limiting reactant or what the limiting reactant is in a reaction? You have a couple of methods, or actually I'm going to introduce two methods. I'm sure there's more that I could introduce, but I'm not, I'm trying to keep it at least as simple as we can, okay? But I want to point out these two methods because they're the most common, and sometimes one of them makes more sense to a person than the other. So I want to introduce both of them, and you can use either of these methods and they'll both give you the same answer. So you don't need to do both. So the two methods are either to compare amounts of reactants or to compare product amounts. Okay, so it's one or the other. No matter which one you do, you have to do some stoichiometry first. Okay, you can't just take the given amounts of substance A and substance B and compare their masses and assume that the lesser one is the limiting reactant. It's not how it works. You can only compare numeric values if they have the same unit, meaning the exact same unit. Not only that it's grams or moles, but also of the same substance. Okay, so when I say comparing reactant amounts, you would be converting one reactant to another. Okay, so if you're given an amount of substance A and an amount of substance B, you could take that substance A and calculate how much B is needed, and then you would compare how much you determined you need with how much you actually have of substance B, and that would tell you, is B your limiting reactant, okay? If what you determine you need, if how much you determine you need is actually more than what you have, then that substance is limiting. If what you need is less than what you have, then that is in excess, okay? Now that method, I would caution you, tends to confuse people a bit more than the other method. So I usually say use the second one, but honestly, it's totally up to you. You can use either one, whichever one makes more sense to you. The other nice thing about this next method is it will not only help you determine the limiting reactant, but also a thing we call theoretical yield, which I will talk about more in the next video. So let's see, if you want to compare product amounts, what you need to do is you take your starting amounts of each individual reactant and you convert them to a product. Okay, so you calculate how much product you could form from each thing. Okay, and then you compare those product amounts, and whichever one produces the least, so whichever one comes out to the smaller value, wherever that came from is your limiting reactant. Okay, whichever ones produce more, those are going to end up being in excess. Okay, so let's do several calculations, okay, to determine limiting reactants for a few different reactions. So this first one I've got, it says, what is the limiting reactant when 3.75 moles of tetraphosphorus hexoxide reacts with 7.25 moles of oxygen gas? Okay, so now we have information about each of our substances. So I'm telling you we have 3.75 moles of P4O6. So I'm just going to go ahead and list that below there so I make sure to keep this straight. And then my O2, I have 7.25 moles. Okay, and I want to know which one of those is limiting, meaning which one of those runs out, or which one of them limits how much product I'm going to get. Okay, so we have two methods. We can compare reactant amounts if we want. And so I'll show you doing that. So if you want to compare reactant amounts, you need to pick one of your substances. So I'm just going to pick P4O6 because it's the first one, okay? But you can do the other one if you really wanted to. 3.75 moles of P4O6, and I would convert that to the other reactant. So I would convert from moles of P4O6 to moles of O2, okay? And so O2 has a coefficient of 2, so I put 2 in the mole ratio, and P4O6 is 1. So that was going to cancel that. And then if I take 3.75 and I multiply by 2, what do we get? It should be 7.50. Okay? And that's moles of O2. Okay? And this is what is needed. Okay? That's what's needed. And then here, the 7.25 is what I have. So I need 7.50, and I actually have only 7.25 moles of oxygen. Okay, meaning I don't have enough oxygen to fully react to P4O6. So that means in this case that O2 is limiting. Okay. So that's how you do that. Like I said, we could have picked the other reactant. You could have picked the 7.25 moles of O2. The difference would be you would convert that to P4O6, and that would tell you how much P4O6 you need, which then you could compare to the 3.75 moles of P4O6 that you have. Okay? So it doesn't matter which way you go with that, but you've got to keep straight what each of those values means. Which one is how much you actually have versus which one is how much you would theoretically need to react the other substance. Okay, so that's one method that you can use. The other method, converting to products, you're actually going to do two calculations. So I know some people don't like to do this method because they feel like it's more work. But remember I said this could answer a follow-up question, which most of the time we want the answer to, okay? So that's why I usually do it this way, because it answers two things at once. So we're going to take that 3.75 moles of P4O6, and we're going to convert it to product, okay? So we're going to go from moles of P4O6 to moles of P4O10. And that, from the reaction, it's 1 mole of P4O10, 1 mole of P4O6. So I would produce 3.75 moles of P4O10 from my P4O6. And then I'm going to take the other reactant and also convert it to product. Okay, so the 7.25 moles of oxygen, and then I want to get rid of moles of oxygen. I want to convert that to moles of P4O10. Okay. And so I look at the reaction, and it's a 1 with the P4O10 and a 2 with the O2. That's going to cancel my moles of O2, just like this first one canceled my moles of P4O6. And so 7.25 divided by 2, what does that give us? That's something like 3.67 moles of P4O10. And so now what you have to do is you have to compare those product amounts, and whichever one's lower, which in this case would be the 3.67, wherever that came from is your limiting reactant, okay? So that tells me that this is my limiting reactant, okay? So really what those numbers are telling me, the 3.75 moles of P4O10, that's how much P4O10 I would get if the P4O6 completely reacts, okay? and the 3.67 moles of P4O10, that's how much I would get if the oxygen completely reacts, okay? But you have to keep in mind, in order to produce P4O10, I have to have both reactants, okay? And so whichever one of those can produce the least, that means once I've produced that, I'm out of that reactant. So once I've produced 3.67 moles of P4O6, I don't have any more oxygen. So I can't produce any more P4O10, okay? Meaning the oxygen is my limiting reactant. So that method also gives you the limiting reactant. So there's lots of ways you can determine. And so most of the time, I would use that second method only because it determines what we call the theoretical yield also as well, right along with determining the limiting reactant. So that can be helpful. But you use the method that you feel more comfortable with. Either way is perfectly fine. We'll do a couple more examples. I'll go ahead in those examples and do one by the reactant method and one by the product method. Okay, so here I say, what is the limiting reactant when 50 grams of iron reacts with 50 grams of oxygen gas? Okay, now sometimes people look at this and they'll say, well, I have 50 grams of each. So that's a stoichiometric amount because, well, the reaction is, you know, just iron and oxygen, and I have 50 grams of each, same amount of each, so it must be the stoichiometric amount, so there's no limiting reactant. Well, that's not true because I'm giving you information about grams, okay? And since it's information about grams, you can't directly relate it to the chemical equation, and you can't just say it's equal amounts, okay? Because what matters is the moles, and also what matters is the ratio that they need to react, okay? And if you look at that reaction I just gave Fe plus O2 going to Fe2O3. It's not balanced, okay? So first we want to balance this, and to balance it, I'm going to need to, well, balance the oxygen. I need 3 oxygens on the one side and 2 Fe2O3s on the other side, meaning I need 4 of the iron, okay? So that gives me 4 irons on both sides, and that gives me 6 oxygens on both sides, okay? And that's the lowest ratio I can do to balance that reaction. So that tells me I need a 4:3 ratio of iron to oxygen, but that's in terms of moles. So I still can't just assume a limiting reactant from the grams. I'm gonna have to do calculations, okay? And so we'll just go ahead and do this using the reactant method. So comparing the reactants. So we can pick either one of these. It does not matter. Let's just pick oxygen gas and start with that. So if I take the oxygen gas, 50 grams of O2, and convert that to iron, okay? So to convert it to iron, I need to be in moles first. So I'm in grams, I need to do a gram to mole conversion, okay? And there are 32.00 grams in 1 mole of O2, okay? Because each individual oxygen is 16.00. So that's going to cancel my grams of oxygen. Now I can convert my moles of oxygen to moles of iron. That way I can figure out how much iron I need in order to react to this oxygen. So I look at the reaction, and there is a 4 with iron, and there's a 3 with oxygen. Let's see. Next up, since the iron that I have is in grams, I'm going to convert the iron that I need into grams as well, so it's easier for me to compare. Okay, so I'm going to convert my moles of iron into grams of iron. And so to do that, I need the molar mass of iron. So if you look on the periodic table, it should 5.85 grams per 1 mole iron. So that's going to cancel my moles and give me the grams. Okay, so I'm going to take 50, divide by 32, multiply by 4, divide by 3, multiply by 55.85. So it looks like I get 116 grams of iron. So that now I'm going to compare to what I have. So here, this means I need 116 grams of iron to react 50.0 grams of O2. Okay, but I have 50.0 grams of iron, meaning I don't have enough iron to react all of my oxygen. That means that my iron is my limiting reactant. Okay, so there we go. Now, that method definitely is, I would say, faster if all you want to know is the limiting reactant. But as I said, that one, people tend to get confused because you have to know what number's what. You have to know the 116 isn't what you actually have, that's what you need, and you don't have enough, meaning it's limiting. But if that number came out lower, then that would mean you have plenty of iron, and that would mean the other substance is limited. Okay, but in this case, iron's limited. Okay, let's do one more example, and we're going to do it using the other method. Okay, so now I have a different reaction. I have a reaction of iron 2 oxide with aluminum, forming iron and aluminum oxide. Okay? And I tell you that we've got 10.3 grams of iron 2 oxide, so I'll just go ahead and list that here, 10.3 grams. And we've got 5.73 grams of aluminum. When those react, I want to know the limiting reactant. Okay, so we're going to do the product method. We're going to take each of these values and convert them to a product, figure out how much of that product can be formed. Now, this reaction, it has two different products. It has a product of iron and a product of aluminum oxide. And it doesn't matter which one you pick. The key is you have to convert everything to the same substance, okay? So I'm just going to go ahead and convert them both to iron, okay? So I'm going to take the 10.3 grams of FeO, and I'm going to figure out how much iron it would produce if that reacts completely. So I'm going to convert my grams first to moles because I can't use the balanced chemical equation until I'm in units of moles. And then next, I'm going to convert the moles of that iron 2 oxide to moles of the product, and I chose iron. Okay, you could choose aluminum oxide if you want, but I'll do iron. And then I'm going to convert moles of iron to grams of iron. Now, you actually could stop at moles here and compare mole amounts. That would work as well. But I'll go to grams because most of the time we want to know the grams anyway. And then this next one, I'm going to do the 5.73 grams of aluminum. I'm going to convert that to the same product. So again, I need to go from grams of aluminum to moles. And then I'm going to convert my moles of aluminum to moles of the same product. Okay, so in this case, iron. If you chose to do aluminum oxide, you would convert it to aluminum oxide. Okay, but it doesn't matter which one you pick. You just need to convert both to the same substance. And then again, I will convert it to grams of that substance. Okay, now I just set up all the units. Okay, I still need to fill in the numbers. So hopefully you weren't too confused there. This is how I usually would do it, is set up all my units, fill in the numbers, then do the calculation. okay? Because your first focus should be the units. You should focus on setting up the ratios to where the units you don't want cancel and you get the new unit of the thing you're looking for, okay? So let's look at these ratios that I have. The first ratio I have relates grams and moles of iron to oxide, okay? So that means I need the molar mass of iron to oxide. So one iron is 55.85 and one oxygen is 16.00. So I add those together and it tells me the molar mass is 71.85 grams per 1 mole. Okay. And then the next ratio is a mole to mole ratio between iron and iron 2 oxide. So the iron has a 3, the iron 2 oxide also has a 3. Okay. And then the next ratio is relating grams and moles of iron. So I need the molar mass of iron. So that's just 55.85 grams per 1 mole. So that setup is going to cancel my grams of FeO. It's going to cancel my moles of FeO. It's going to cancel my moles of Fe and give me grams of Fe. So I'm going to go ahead and type that in. 10.3 divided by 71.85 times 3 divided by 3. So you can skip that if you want. It's just multiplying by 1 essentially. And then times by 55.85. Okay, so that gives me 8.01 grams of iron. And then my next one, I still need to fill in my numbers. Okay, I got my unit set up. My first ratio relates grams and moles of aluminum, so that's a molar mass. So you look at the periodic table, and it's 26.98 grams per mole of aluminum. And then you need your mole-mole ratio, so you look at the balanced chemical equation. You put a 3 with the iron and a 2 with the aluminum. And then the last ratio is gram to mole relationship of iron, which again is 55.85 grams per mole. So this all is going to cancel my grams of aluminum, my moles of aluminum, and moles of iron and give me grams. Oops. Fine. And so we can type this in a calculator and get 5.73 divided by 26.98 times 3 divided by 2 times 55.85. And that gives me 17.8 grams of iron. So what these calculations are telling me is if I react 10.3 grams of iron to oxide, I'm going to get 8.01 grams of iron. If I react 5.73 grams of aluminum, I'll get 17.8 grams of iron. Okay? But each of those calculations is only true if I actually have enough of the other thing. Okay? And so all you need to do is look at which one produces the least. Okay, so 8.01 is less, meaning your iron to oxide is your limiting reactant. Okay, and so once the 10.3 grams of iron to oxide produces 8.01 grams of iron, you're out of iron to oxide. Okay, and in that reaction, it's going to be consuming aluminum. But at that point, since you're out of iron to oxide, you can't produce any more iron, okay? So even though there's going to be some remaining aluminum, you can't produce that 17.8 grams of iron because you don't have enough iron to oxide. So the iron to oxide is our limiting reactant.